Hello, my name's Colin, and I'm a principal consulting engineer at Nokia. And today we're going to talk about Evpn. Well, I'm going to talk a little bit now, and I'm going to cut to a video I shot 2 years ago. The reason for that is that this video is great, and I wanted to repost it here on my new channel. It also aligns with some of the stuff we're doing here at Nokia with some of the training and enablement we're putting together around our data center solution. And I didn't feel like recreating all these slides. So I had to reshoot the intro and reshoot the outro because I was wearing a Juniper shirt in that video. Aside from that, none of this is vendor specific. We're just talking about Evpn. And the intent of this video, both when I recorded it and now, was to convince you, the audience, that if you already have foundational understanding of how networking functions, the learning and forwarding that switches and routers do, you already know most of what you need to know for Evpn. All right. All Evpn is, like most routing protocols, is a way of distributing a control plane, local information used for forwarding traffic. It takes that and it distributes it. Right. So I'm going to show you first with a basic overview of routing and switching, just kind of remind us of our terms and kind of the default behaviors we see with normal traditional network. I'm going to show you how the traditional things we already know align with the route types that Evpn uses to distribute the control plane information. So I'll see you at the end of the video, and in the meantime, enjoy 2-year-old me. Beautiful. Whoops. That was 7-year-old Owen. I meant enjoy me from 2 years ago. I don't think I have any video of me when I was 2. All right, see you at the end. First, a quick review. And I want to point this out because I have been asked this a few times. Remember that even if you have a switch running on layer 2, the hosts that you plug in are going to be functioning at layer 3. They're going to have an IP stack. That IP stack is going to be configured with an IP address and a subnet at the very least. If there's no gateway, it's only going to be able to communicate with hosts that are on the same subnet. If it has a default gateway, it'll attempt to first resolve and reach that default gateway, and then any traffic destination that isn't in the same subnet will be sent to that gateway for routing. If you already understand the basics of this, it all makes sense. I am going to do a quick review because I do want to reinforce the different elements here that a switch/router does when a host gets plugged in and tries to forward traffic so that I can connect them to what Evpn is doing. Let's just say we've just plugged a host in. Host sends a packet. The packet has a header. Here's a section of that header. It contains a source MAC address and a destination MAC address. And that's because we're here at layer 2. It will also contain a source IP address and destination IP address, again, regardless if the switch is layer 2 or not. But right now, since we're at layer 2, we're just focused on those MAC addresses. The first thing the switch does is it sees this source MAC address and it programs it into an Ethernet switching table, a catalog of learned MAC addresses that are connected to an interface. And this is information that is distributed, but it's stateless, which means that you have two switches connected to each other and you plug a host into one of those switches and it programs this into the table. The switch that's connected to it isn't going to get that information. The way that it's going to learn it is a packet will be sent from a host on a different switch that will go and cross to the second switch. And that second switch will see that packet and then it'll learn it. It'll associate it with the interface that's connected to the downstream switch the host is connected to. The forwarding mechanism, it looks at the destination MAC. It either knows it or it doesn't. If it doesn't know it, we go over here to where we have flooding. It is important to point out that if you are using VLANs, those VLANs will also be added to the Ethernet switching table. If you're not using VLANs, they'll go in the default. This flooding activity is defined by what we do with BUM traffic, BUM. You're going to hear this term a few times today. BUM stands for broadcast, unknown unicast, and multicast. In this case, assuming that this is a host-to-host communication, it's going to be unknown unicast if I don't have the information I need to forward it at layer 2, which means that I will flood that traffic out every interface except the one it was received on. If I'm running VLANs, then I'll flood it out every interface associated with that VLAN except the one it was received on. There's filtering. Filtering is just a mechanism to ensure that we don't have excess churn, excess data on the network. I haven't seen a hub in 15 years, but this is a pretty good example. I have a packet that comes into this switch, and in my Ethernet switching table, I see the destination for that is the same interface that it came in on. I'm going to drop it. Finally, aging. If you unplug a device, there's got to be some way of clearing out this information because obviously it's not connected. Layer 3, we use ARP, the address resolution protocol. Packets that cross the network and they hit a layer 3 device, that layer 3 device will program that into a table, the ARP table. That includes interface it was learned on, VLAN if there's one associated with it, the IP address, and the MAC. Evpn takes the control plane information and it shares it with other devices that are configured in the same fabric. It does this through the advertisement of routes, and depending on the information that it is attempting to distribute, we have different route types. We're not going to talk about type 6, 7, and 8 today. Those are all related to multicast, and so is type 3. A little bit on that later. The multicast forwarding route types we'll get into as we get into the larger campus designs, but not for the MC-lag conversion. I'm not going to go through these in numerical order. I'm going to go through them in order of relevance. Because of that, I am going to start with type 2. Simply put, type 2 routes are for host reachability. In the same way that we saw legacy networks learning MAC addresses and IP addresses, Evpn as a protocol is snooping this information off of packets that come into the fabric and programming it both into local tables and into route advertisements that are then distributed to the other fabric switches. On its own, the MAC and IP address isn't enough for reachability. And that's because VXLAN is a tunnel. That means it abstracts all of the network hops in the middle, which means the next hop when I come in here to get to site 2, host 2, is the tunnel endpoint over here. Well, how do I know that host 2 is connected to this switch? In a traditional non-fabric network, I know that because in order for this information to propagate over here, I have a path. It comes through all this other stuff, which means that this leaf 2 here would know that it learned that IP address or MAC from this spine 2. It would associate it with that interface. Not so with a VXLAN tunnel. So we need a bit more information. We need to know that these hosts are connected to their respective switches. And beyond that, we need to know what routing instance, or VRF, the interface this host is connected to is a member of. Routing interface, that's for segmenting the routing tables for the networks that you're putting into your fabric. A routing instance can have one subnet, it can have many. The common use case for this in a campus environment would be isolation of forwarding. You might want to keep your guest network completely, from a routing perspective, separate from your CorpNet, from your facilities, and so on. So we need to have a bit more information than just the IP and the MAC address in this type 2 advertisement. If we look at the information that is included in the advertisement, we start to get a sense of how this is done. We'll start off with the route distinguisher. The route distinguisher is a value that can be expressed in one of two ways. Really, I'm going to focus on one. You can use an ASN as a component of the route distinguisher. More commonly, what a route distinguisher looks like is a standard IPv4 address, followed by a colon, followed by an integer value. That IPv4 address can be anything, and I'm shrugging. I mean, you can make it what you want, but there is some deterministic logic you probably want to apply. Let me walk you through what that means. All of the devices that are in this fabric are going to have loopback interfaces configured. Those loopbacks are going to have unique IP addresses. You're also going to have router IDs configured. These router IDs are used to uniquely identify a switch within the fabric network. Normally, you want to make your router ID match your loopback interface IP, and specifically the loopback that is in the default instance. Now, we have a way of knowing which switch is leaf 1 and which switch is leaf 2. So typically, your route distinguisher, you're going to match that router ID. With the router ID, we now know that host 1 is connected to this switch and what routing instance it's in. So we take that information and we distribute it to the rest of the fabric. This route advertisement is also going to include the VXLAN VNID. This is an odd way of putting this. VNID is usually expressed as VNI. It means VXLAN Network Identifier. This is essentially a mapping from the network segment, the VLAN, to a value that is placed into the VXLAN header. And then at the other end, it gets pulled off. Best practice for me, just match your VLANs to your VNIDs. There's going to be talk about how you can have 16 million VXLAN VNIs. You're not going to have more VNIs than you have VLANs in your network. So just make it one-to-one. So if you look at a VNI, you know the VLAN it's associated to. Easy peasy. The Ethernet segment we'll talk about later. What you need to know now is that anytime you have a host that is single homed to the fabric, this value will be all zeros. We'll talk about multi-homing later. For most campus applications, you don't have multi-homed hosts. It's far more common to see multi-homing in a data center environment where you have servers that have multiple Ethernet cards that are plugged into multiple switches. I know I said we weren't going to talk about multicast. This is really just an overview of how BUM traffic is handled. Remember, BUM is broadcast, unknown unicast, and multicast. In the absence of multicast routing configuration, we use what's called ingress replication. And the reason, just think about it like this. If I send a broadcast frame into the fabric from this host, I do need to make sure that it reaches all of the other hosts that are on the same subnet. So here we only see 2 hosts. Imagine that there's a bunch more over here somewhere. That replication of those packets takes place on ingress to a switch where there are multiple endpoints. So in this case, I'm really sending only 1 frame, but if I had other switches that had other hosts, then when that packet reached that other switch with multiple connected hosts that broadcast frame needed to reach, then it would replicate that packet and forward it. If we're using multicast, we might have PIM configured that can reduce a bit of the chatter. We're not talking about multicast, so all you need to know is that these type 3 routes are there to advertise to the rest of the fabric devices how the BUM traffic is being handled and provide a address for the local device that's originating the route advertisement, so that if you're sending BUM traffic in the direction of that switch, in this case, let's say it's leaf 1 and leaf 2 sending it information, it knows what that destination needs to be. I know I said that you're not going to have a lot of multi-homed hosts in a campus network, but that doesn't mean you won't have any. Enter the type 1 EVPN route. If you have any familiarity with EVPN VXLAN, you might have heard the term ESI lag. This is the method used to synchronize a LACP control plane. Basically, anytime this value, this ESI value, is non-default, which is all zeros, or it's not using one of the reserved addresses, which I think there are, but I couldn't tell you what they are. Just if this is a non-zero value, a type 1 route will be generated. This ESI value identifies the links that are members of the same bundle. You obviously might have multiple bundles, and JUNOS, the language, would be an aggregate Ethernet interface on the same pair of switches. So you have maybe 4 or 5 hosts that connect to the same 2 switches. And in fact, it doesn't even need to connect to the same 2 switches. That's kind of the coolness of ESI lag, is that you can configure these ESI connections within your AE configuration anywhere you want. As long as your hosts are plugged in where they're supposed to be, it'll work. These routes will get generated, they'll get propagated, and it basically tells the rest of the network, if you want to get to this host, you can send traffic here, or you can send traffic here. This advertisement also includes a flag. It's called the single active flag. It indicates the multipath capability. We only support setting that flag to 0. You're not really going to be tested on this, so to speak. Just know that we only support active-active multi-homing. There is built into the standard the capability for active standby multi-homing, but that's not really multi-homing because it means you're only really using one path at a time. So we have all active, which means you can use either of these paths and load share your traffic across them. When you're multi-homing, the ESI value in the type 2 route, the MAC IP route that we looked at before, is different as well. I just do want to highlight that. It was all zeros in the example I used. It's not enough to just propagate that this exists. We need to know which hosts are actually connected to it as well. And like I said before, this goes into the AE part of the configuration. So you'll build your aggregate interface as you would any other time, and then you'll actually have specific ESI configuration that is used by EVPN. Once configured, Remote switches will consider all remote tunnel endpoints associated with the same ESI as valid paths for the MACs that are associated, or the MACs and the IPs, essentially the hosts that are associated with that ESID. Type 1 routes also give us fairly fast convergence. If we have a link failure here, in this case, we're seeing a link failure to leaf 1, the type 1 route will be generated with a withdraw for all of the host MACs and IPs that are associated with this ESI link, this specific link here, rather than having to pull all of the associated MACs and IPs. And you might see one host here, but imagine this was a VM host and there was like a bunch of guests on it. Having 1,000 MAC IP, basically type 2 routes withdrawn, is going to take a heck of a lot longer than sending a single type 1 route that withdraws the endpoint for those associated MACs and IPs, so that there's only, in this example, one path that remains. It's just a lot more efficient. Before we talk about type 4 routes, we're going to talk a bit about split horizon protection. We see the leaf here receiving bum packets. It floods to local hosts on the same VLAN. It will flood to remote leaf nodes in the same VLAN, but it will not flood back to the original device. In your typical network, think about bum traffic. You send it out every interface that's associated with the ingress VLAN except the interface that it was received on. Pretty straightforward. That's actually very similar to what we have in a traditional network. If a leaf receives a bum packet from a remote leaf, it will flood to local hosts on the same VLAN. Makes sense again. It will not flood traffic to remote leaf devices. In this way, we know that the leaf that originates that bum packet is the only leaf that's allowed to forward it to all other leaves. If a leaf receives a bum packet, it'll forward it locally, but it will not forward it back to other leaves. This is going to prevent you from creating a broadcast storm. It's not perfect though. In the scenario here, if we look on the left, there's a single homed host and a multi-homed host. The single homed host sends a bum packet to leaf 1, which performs ingress replication, sends a packet to leaf 2, sends a packet to leaf 3. Both leaf 2 and leaf 3 see it's connected to them directly, forwards the packet. Now host 2 gets 2 copies of the same packet. That's no good. Now on the right, we're going to do this in the opposite direction. Let's say the multi-home source sends a bum packet to leaf 3. Comes right here. Now, it could just as easily send it to leaf 2. It's LACP at this point, right? So there's a round robin. We're just saying send it to leaf 3. Leaf 3 gets the packet, sends it up to leaf 2, sends it to leaf 1. Now, leaf 2 won't send it to leaf 1 because remember the rule is if I didn't originate the bum packet, I won't forward it to other leaves. But it sure as heck is going to forward it back to the source. It doesn't have any mechanism to know that packet originated from the source. So host 1 will get that packet like it's supposed to, and the source will get a copy, I guess, to save for later. Again, we don't want this. The way we deal with it is by creating a designated forwarder. Now, you might have heard this term before. If you're familiar with OSPF, it's not the same. It is a way of optimizing communications, but it's not doing the same thing that OSPF is doing, which is essentially optimizing multicast signaling. In this case, the designated forwarder is a device that is, as it says on the screen, elected to forward traffic towards a multi-home site. This election uses type 4 routes, which we'll start talking about on the next slide. What you need to know now is that once that election is made, all bum traffic for a destination Ethernet segment will be sent to the DF only. The DF also prevents traffic sourced from a multi-homed host from being forwarded back to that host on the same ESI. When a multi-homed host is configured and an unreserved ESI value is defined, again, non-zero value is defined, the devices the multi-homed host is connected to generate type 1 and type 4 routes. That would be these two devices here. It also creates a import rule and a community. That community is unique to this ESI value. You actually see it sort of expressed here, ES import. That's important because the type 4 route will propagate throughout the fabric, but because there is a community that is specific to that ESI value, that community doesn't exist on leaf 1. Leaf 1 will drop the type 4 route. The type 4 routes then are exchanged between the two switches, and that election is then completed. If you are in two separate fabrics and you are not stretching your L2, then you don't need to learn every single discrete host IP. You can learn prefixes. That's what Type 5 routes do. They allow you to essentially summarize reachability information between two discrete fabrics with non-overlapping subnets. It can greatly reduce the size of your route table. Most of the time, you're not going to directly connect different campus networks in different geographical locations. You might have different buildings or something, so there might be a use case for Type 5 routes at some point, but rarely do I see a campus network directly connected to a campus network in a separate location. You'll have some intervening core, you'll have WAN links, you'll do traditional routing. Those campus networks are just a way of optimizing configuration and maybe implementing things like microsegmentation locally. See? Not that scary. I mean, it can be complex like anything. This isn't meant to be the definitive guide, but I did want folks to understand that if you have a foundational understanding of networking, you're already so close. You're already so close to understanding how the Evpn works. You layer VXLAN on top of it, which is a forwarding plane protocol, and that's how you get most data center fabrics, where you have the Evpn control plane, which is learning where everything that connects to the network is and programming the tunnel endpoints that VXLAN uses. This is Data Center 101, what have we been trying to do for the decades that we've been building data centers. Every protocol is an effort to make hosts that are separated by geography, whether in different racks, different rows, different buildings altogether. We want those devices to feel like they are right next to each other. And we're abstracting geography. We're allowing ourselves to stretch broadcast domains across that geography, build layer 2 adjacencies, simplify forwarding. Packet arrives on the leaf switch in the data center, and it goes to one of two places. It goes to another port that's on the switch because wherever it's headed is already there, and it's connected in the same rack. Or it goes to a tunnel. That's your two options. And when it enters that tunnel, it comes out where its destination is. And boy, that makes a lot of things easier. There'll be more of these. I do feel now that I'm about 4 months in at Nokia that I can start getting back towards a regular cadence. I'm also learning enough about their solutions to start talking about them. I hope this helped. Hope it was informative, and I hope to talk to you soon. Take care.